Okay, people, we should make a start. So, nothing too exciting going on there. All the usual stuff. Quiz 5 is due middle of next week. Okay. So, we're on to our very last topic, which is graphs. And so I guess there's one thing to get out of the way here, which is that when we say graphs, we do not mean this sort of thing. So if you talk to a mathematician and they're speaking precisely, they'll say this is a plot or something like that. It is not a graph, at least in the sense that we mean when we say graph theory. So this is not a Bacon graph. This is a Bacon graph, right? So this is a, 6 degrees of Kevin Bacon sort of thing. But basically, it's a network, right? We have nodes in this network, and some of them are joined to each other, others are not. We'll see soon that we'll call the nodes vertices and the connections between them edges. But when we talk about a graph, we're talking about a network, not a plot of a function. I know some of you have seen those before, some of you maybe not. Okay. So, why should you care about graphs? Well, I think they're pretty cool. My own research is sort of graph related. But beyond that, graph theory, I think for lots of really obvious reasons, is used a bunch in computer science. So, for analysing networks, but where by networks I might mean computer networks, but I could also mean a social network or a transport network or whatever else, right? When I was going through my honours at University of Queensland, some recent graduates were hired by the company that the Queensland Public Transport people contracted to sort out their app and all that sort of thing, or at least their website, probably back in those days. But that's not all. Sometimes graphs also are really great ways of representing and solving problems for various algorithms. So one classic example of this is with scheduling or allocation problems. So often it's really good to say, if you're trying to match things here with things here, draw a connection between any pair of them that you can be part of that match and then try and do something. So lots of reasons you might care about graph theory, I think. Okay. So, this is a lecture with lots of stuff in it. Most of it's fairly basic stuff, but even if you've done some graph theory before, this can get quite tricky quite quickly. So, sort of keep your eye on it as we go through. Okay, so basically a graph is going to consist of nodes and connections between those nodes in a network and connections between those nodes. We call the nodes vertices, and we call the connections between them edges. So, as you know, mathematicians and computer scientists are bandits for representing everything with sets, and this is no different here. So formally speaking, a graph is just two sets, two collections. One is a set of all the vertices of the network. The other is going to be a set of all the edges of the network. And edges we represent as unordered pairs of vertices, right? Okay, so I'm going to give you some examples in a minute, but that's the formal definition. It's a set of vertices and a set of edges, but most usually when we're thinking of graphs, we draw the pictures, right? Because that's a lot more intuitive, a lot more human understandable. So being able to go forward and back between the formal representation, which is useful for if you're working with a graph with a computer, or if you're being really formal about talking about a graph, and the picture, which is better for intuition, is important. So, here's some examples of graphs. So, the formal version of this graph is the vertex set A, B, C. People use either capital or little letters here, doesn't really matter. Vertex set A, B, C, and the edge set AB, BC, CA, right? So that means that our vertices, our nodes are A, B, and C, and A is next to B. There's an edge between A and B, there's an edge between B and C, and there's an edge between C and A, right? Where these edges don't have a direction, right? For us, the basic object, edges are not directed, so they're all next to each other. Now, of course, if you start writing many edge sets like this, you get a bit of overkill in terms of curly brackets. So to cut down on that, often people just write edges like this edge AB as AB, right? Which is nice because it means you don't have those curly brackets anymore, but it does mean you've got to remember that AB is still the same as BA, right? We could have written it either way, means the same thing because both of them represent the set containing A and B, right? So, using that notation, here's another graph. Vertex set is now A and B and C and D, and here is the set of edges, right? So this AB is representing this edge, AB here. This BC is representing this edge, BC here, and so on and so on. But notice we can draw lots of different looking pictures of the same graph. So this graph and this graph are exactly the same, right? Because if you check, they've both got this vertex set and they've both got this edge set, and that's all there is to a graph, right? If they've got the same vertex set and the same edge set, they're the same. It doesn't matter where you draw the vertices or if you draw the edges as crossing or not, right? So let me say a little bit more about that. We are allowed, when we draw a graph, to draw edges as straight lines or curvy lines, and also we don't care if they cross over each other. So this and this are two ways of drawing exactly the same graph. It would have the same vertex set and the same edge set, right? And in particular, just because these cross doesn't mean there's a vertex here, right? Just means they happen to cross, right? Now, of course, sometimes people do care about whether edges cross and whatever else, but from a graph theory perspective, they are then studying graph drawings rather than graphs themselves, right? So the basic object has no notion of whether edges cross, of where the vertices are arranged, any of that. All that counts to figure out whether one graph is the same as the other is what are the vertices and which ones are joined by an edge. Does that make sense? Okay. So, question 29.1 in the notes says, write down the vertex sets and the edge sets for the graphs corresponding to the following pictures. Okay, what's the vertex set going to be for all of these graphs? Set containing A, B, C, D. Okay, what are some edges of this graph? C. I think I heard all of them in that. So the vertex set here is going to be the set containing A, B, C, D, and the edge set is going to be the set containing AB, AC, AD, and BC. where you could have written this as CB if you preferred, right? Doesn't matter because edges don't have a direction. Make sense? Okay, so for the center picture, vertex set is the same. Edges are AB, BC, CD, DEA, or AD, whichever you prefer. There they are there. For the right picture, vertex set A, B, C, D. Edge set, what do we notice about these two? So these are exactly the same, which means what? Those two graphs are the same, right? Different drawings of the same graph, right? So if you check it out, you could get from this one to this one by just flipping C and D, which means they're the same thing, right? So you can draw the same graph different ways. Any questions on that? Okay. So 29.2 asks us to draw graphs with these vertex and edge sets. Now obviously you can do these drawings in lots of different ways. Basically you're just aiming to draw it in some way that looks reasonably neat, right? There's no hard conditions for how you're going to do this. So I reckon this first one could look like this, right? It's vertex set A, B, C, D, and notice we've got every edge possible containing B and none of the others here. This next one, I think, looks like this. This is still one graph, right? Even though it comes in two pieces. Towards the end of the lecture, we'll see that this is called a disconnected graph as opposed to a connected graph. But this is still a perfectly valid graph. It just happens not to all be connected into one piece, right? So, any questions on that? Good, good. Okay, so I've got a question for you then. 3 of these are actually the same. Which one is different? Oh, I probably didn't do that right, did I? I'm going to keep you to a fairly tight schedule here because we've got lots of stuff in this lecture, so. How are we doing? Okay, another 20 seconds. Okay, so let's have a look. So, I do actually agree with the majority of you. I think the answer here is B. Now, I think probably the easiest way to see that is that B contains this triangle. We haven't formally defined what I mean by triangle. We'll see in a minute that I could call it a 3-cycle or a complete graph of order 3. But it's got 3 vertices where they're all mutually joined by an edge, right? Any pair of them is joined by an edge. And if you notice in any of these other graphs, you are not going to see that configuration. And you can maybe also see how you get from some of these graphs to others, like in D. If I pick this up and plonk it over on the left here, and then I sort of twist this round, right, I'll get to A. And you could even, I think, get from C to A by putting this vertex, and this vertex up the top, and this vertex, and this vertex down the bottom. So not entirely easy to see, for sure. In general, you know, given two crazy representations of a graph, it can be difficult to know if it's the same. Okay, so this is mostly to talk about things we won't be looking hard at here, right? So there's plenty of different variations you might want to do with graphs under certain situations, right? If you're modeling a traffic network, you might want some of your edges to have directions because one-way streets exist, right? If you're you might, in that situation too, sometimes have two equally good streets between two different places, right? You might want to have multiple edges between vertices. You might want to allow edges from a vertex to itself, right? Now, at the moment, our graph definition doesn't allow any of those because our edges are unordered sets, right? Pairs, unordered pairs, so we don't have direction. We've said that our edges have to be pairs of vertices, as in two, so we can't have edges from a vertex to themselves. And because our edge set is a set, everything can only be in at once, so we can't have multiple edges between vertices. So for us, we're looking at the basic object, and we don't allow any of those added bells and whistles I just talked about, right? But definitely in some applications, people want to include them, and you can do that. And mostly it doesn't change the theory a whole lot, but obviously in places it does, right? But we're going to stick basically with the basic object. We're going to talk about multi-graphs where you can have multiple edges between vertices very briefly in a couple of seminars time, but not much. You can also have hypergraphs where your edges connect more than two vertices. They can be really useful and interesting. Sometimes you want to have your edges have weights or have the vertices have colors, or there's all sorts of things you can do. Just bear that in mind, right? All these variants can be useful and interesting, but the basic object of a graph doesn't have them. So for us, a graph is not allowed to include multiple edges between the same vertices. So two vertices are either joined by an edge or not. There's no joined by three edges, right? And we're not allowed edges from a vertex to itself, which are sometimes called loops, right? They're not allowed either. Now, when people want to include these things, they usually call it a multigraph rather than a graph. Sometimes we say a graph is simple when we want to emphasize that it's not a multigraph, right? But if we just say graph, we mean not a multigraph. We mean simple graph. So simple is just emphasis that it's not multi. But if you just see us say graph, we mean a simple graph with none of these multiple edges and loops and stuff. Is that clear? Awesome. Okay, so let's try and build up a little bit of vocabulary then. So we're going to talk about three or four, I guess, different sorts of graphs that come up all the time. So the first is what we call a complete graph. And a complete graph has every possible edge it could have in it, right? So these are complete graphs with 2, 3, 4, and 5 vertices. So with 2 vertices, you've just got 2 vertices with an edge between them. For 3 vertices, you've got this triangle thing we talked about earlier. All the things are, every pair of vertices has an edge between them. 4 vertices, you have 6 edges. Every pair of vertices has an edge between them. This is what it looks like for 5 vertices, and you can imagine, right? You just keep going. For 6 vertices, you draw 6 dots. You put in every possible edge between those 6 vertices, right? So if a graph looks like that, it's called a complete graph. Notice that it doesn't matter what we label the vertices here, right? We can call them, you know, A, B, C, D. We can call them Fred, Bob, Judy, and Paul. Doesn't matter. If they're if any pair of vertices is joined by an edge, then it's a complete graph, right? Okay, that's complete graphs. So the next thing are going to be paths. And paths, again, hopefully these names give you some intuition as to what they look like. Here's a path with, well, so let's have a quick look at the definition. So a path of length L has L plus 1 vertices. Now we don't care what they're called, but what's important is that we could label them V1 up to VL plus 1. And then if we did that, our edges would be between V1 and V2, between V2 and V3, between V3 and V4, blah, 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 all the way up to VL and VL plus 1. So we could sort of put it all in a line, is the idea here, right? So here's a path of length 1. Notice that the length counts the number of edges, not the number of vertices. Right, so this is a path of length 1, but it has 2 vertices. This is a path of length 2. This is a path of length 3. This is a path of length 4, where obviously we could draw these in lots of different ways, but the important thing is you could string it all out into a line if you wanted to. Make sense? Okay, that's paths. So we've done complete graphs. We've done paths. Next thing is cycles. So these have just one more edge than the sort of the paths did, really. So and notice again, we don't care what the vertices are called. All that matters is we can string them out into a line. Here, all that matters is that we can put them in a circle kind of thing, or a cycle, if you like. So again, a cycle of length L has L vertices now, and we should be able to relabel them, if we wanted to, V1 up to VL, so that our edges are V1, V2, V2, V3, all the way up to VL minus 1 VL. That puts them in a line, but then we also have an edge from the end to the start, from VL to V1, right? Or between VL and V1. So there is no cycle of length 1 or 2. Here's a cycle of length 3. Here's a cycle of length 4. Here's a cycle of length 5. Here's a cycle of length 6. Again, we don't care what the vertices are called as long as you could draw them like that. It's a cycle. And notice now that again the length refers to the number of edges, but now this is the number of vertices as well, right? So a cycle of length 6 has 6 vertices. Any questions on any of those? I know we're going through these fairly quickly. Got a bit to cover today. Okay, so this is our last sort of piece of vocabulary. It's a little bit trickier than our other types of graphs. So there's a sort of graph we call bipartite. And this is a much wider class of graphs than the last few we've talked about. So a graph, so bipartite, we're thinking two parts, right? And that's what you want to be thinking here. A graph is bipartite if we can divide its vertices into one chunk, which, say, we could label these ones U, and we could label the other chunk of vertices with various V's, and then every edge should be between the chunks, not within the chunks, right? So here, I'm drawing them as one chunk, or one, they're called parts, so I'll start calling them parts, one part on the left and one part on the right. And what is important here is that there are no edges living entirely on the left and no edges living entirely on the right, right? Some of the edges across will be there, others might not be there, that's fine. So bipartite, if you can, notice that this is if you can arrange it. It doesn't have to be arranged like this in the picture you see. If you can rearrange it to have these two parts with no edges internal to either of the parts, then it's bipartite. And then one more thing, complete bipartite is a bipartite graph that has every possible edge it could subject to being bipartite, right? So here, this is a bipartite graph with one part of size 3 and another part of size 3. It's got every single edge between the parts present, but of course, because it's bipartite, there's no edges inside the parts, right? And same here, this is a bipartite graph with parts of sizes 2 and 4. This is a bipartite graph with parts of size 1 and 3. Yes, question?
Can we tell a bipartite graph if it's scrambled?
Okay, the question was, can we tell a bipartite graph if it's scrambled? The answer is there is actually an easy test, and we're going to see it in about 20 minutes or something. So yes, there is a fairly quick way of telling. But of course, it might be scrambled and it could still be bipartite. So you've got to be aware of that. Any questions on that? So if you check, this is a little bit of foreshadowing. Paths are always going to be bipartite, right? Because we can always draw a path like that, right, across. Even cycles are going to be bipartite. We saw before that a cycle of length 4 we can draw as that, right? Same sort of thing goes for other even cycles. Odd cycles are not bipartite, and we're going to talk about that in a minute. So, roughly speaking, a graph is bipartite if we can divide its vertices into left and right parts, so there are no edges on the left and no edges on the right. So, is this graph bipartite? Who thinks yes? Who thinks no? I think yes, right? I can draw it so that it's got two vertices on the left, two vertices on the right, and there's no edges on the left and no edges on the right, right? So it doesn't matter how it's drawn for you. The question is, can you redraw it? Does that make sense? Is this bipartite? Who thinks yes? Who thinks no? What kills us here? This cycle of length 3 kills us, right? Because no matter how we divided this into two parts by the pigeonhole principle, I guess, 2 out of A, B, and C would have to be in the same part, and then we'd have an edge in that part. Make sense? So this one, definitely not bipartite, right? How many edges would there be in a complete bipartite graph with parts of size I and j? I times j, right? Because in a complete bipartite graph, we're going to have every single edge between the part on the left, which is size I, say, and the part on the right, which is size j, say, and there are I choices for the vertex on the left and j choices for the vertex on the right. Okay. So, ij edges there. Okay, so question 29.3. What's the maximum number of edges that a bipartite graph with 6 vertices can have? And in general then, what's the maximum number of edges that a bipartite graph with n vertices can have? So who's got a thought for 6? What's the most number of edges we can cram into a bipartite graph that has 6 vertices in total? I heard 9. Why is that? Okay, so the idea is we're going to split it 3 and 3, and I think that's a good idea. So because we're trying to cram as many vertices in as possible, we may as well make this a complete bipartite graph. So how could we split our 6 vertices? Well, we could split them into parts size 1 and 5, but that would only give us 1 times 5 edges. We could do 2 and 4, that would give us 8 edges, but if we go 3 and 3, we can get 9 edges, right? And obviously the other options are 4 and 2, which give us 8, and 5 and 1, which give us 5, right? So 9 is the most we can have, yeah.
Is there a formula for that?
Is there a formula for that? We're about to see it, yes. Okay, so the next part of the question is what's the maximum number of edges that a graph with n vertices can have? Well, it's going to turn out that in general, this is our best strategy, right? Split it into equal-sized parts. So if n is even, that's easy, right? We should choose 2 parts of size n on 2. How many edges is that going to have? N on 2 times n on 2 is n squared on 4, right? Now, if it's odd, what should we do instead?
Have 1 part here less and 1 part here less.
Yeah, so have the 2 parts differ only by 1 vertex, right, in terms of the number of vertices. So one part is going to have size n minus 1 on 2. The other is going to have size n plus 1 on 2. So this is like splitting an 11 vertex graph 6 and 5, say, or 5 and 6 in this order. And then that is going to have n squared minus 1 on 4 edges if you multiply those two, right? So there's your formula. Does that make some sense? Cool. That's obviously only a maximum, right? A bipartite graph could have, on n vertices, could have any number of edges up to that, right? Because you could start with one of those and just delete some edges if you wanted to. It'd still be bipartite. Okay, so I think we've got like 2 more concepts in this lecture, and then we will talk about something a bit fun. So the next thing is a subgraph. And a subgraph, again, a bit like a subset is a set that sort of lives inside another set. A subgraph is a graph that lives inside another graph, right? So a subgraph is a subgraph if, so you're a subgraph of G if your vertex set is a subset of the vertex set of G and your edge set is a subset of the edge set of G. That's sort of the formal way of saying it, right? The informal way of saying it is that you're a subgraph of a graph if I can go from that graph to you by, if I want to, deleting some vertices and some edges, right? So here, this graph is a subgraph of this graph because I can get from here to here by deleting D and this edge and this edge and this edge and this edge, right? So I deleted a bunch of vertices and edges. I got from here to here. That means this is a subgraph of this. Does that make sense? And of course, we could think of that in terms of vertex set and edge set. Here our vertex set is ABC, which is a subset of the vertex set ABCD here, and our edge set is AB and BC, which is going to be a subset of the big edge set here, which has 6 edges, right? Okay, so I think that, oh, and notice every graph is a subgraph of itself, right? So we don't have to delete anything. A graph is always going to be a subgraph of itself, just the same way every set is a subset of itself. Okay, and just as we're sometimes a little bit lazy when we talk about graphs or save ourselves being too wordy. So sometimes we'll say a graph G contains a cycle of length 5. If you wanted to say that super formally, you'd be saying G has a subgraph that is a cycle of length 5, right? Means this is just a slightly shorter way of saying that. Or similarly, there is a path of length 6 in G, is G has a subgraph which is a path of length 6, right? So we let ourselves be a tiny bit informal with that. Any questions there? Okay. So here's a question. I've pictured the graph for you. So it says, let G be a complete bipartite graph with parts of size 2 and 4, right? So here it is. Here's our part of size 2, here's our part of size 4, every possible edge, because it's complete bipartite between the two. Which of these is true about the subgraphs of G? So I'll give you a minute to think about that. Good one to talk about for a second. I'm going to keep you on a fairly tight schedule, but should be able to hopefully spot that some of these are wrong for various reasons. How are we doing? Okay. Another 30 seconds or so. Okay. So, I do like that as an answer. So let me point out why I think some of these are wrong. G contains a complete graph with 4 vertices. That can't be right because 4 vertices is going to definitely have either 2 on the left or 2 on the right or both, and those are not going to be joined to each other by an edge, so it can't be complete, right? So C's wrong. D is wrong because there's no cycle of length 3 here, right? We'd have to be able to go 1, 2, and then 3, or 1, 2, and then 3, but we can't do that because it's bipartite. So D's wrong. A is wrong. There's no way you can cram a cycle of length 6 here, right? I can see a cycle of length 4, 1, 2, 3, 4, but a cycle of length 6 would have to have 3 vertices on the left and 3 on the right, and we don't have enough vertices. So all that leaves is B, and there definitely is a path of length 3, say 1, 2, 3, and there is a path of length 4, say 1, 2, sorry, I started that the wrong way, 1, 2, 3, 4, right? To find a path like that, you're going to have to start on the right, but such paths do exist. Does that make sense? Okay. So subgraphs are useful because sometimes you can say a lot about a graph by thinking about its subgraphs. So to come back to the question I was asked a little while ago, can you tell if a scrambled up graph is bipartite or not? One really good way to tell if a scrambled up graph is bipartite is this. I guess this is our first sort of graph theory theorem. It turns out that a graph is bipartite if and only if it doesn't contain odd cycles, right? Doesn't contain any odd cycle or has no subgraph which is an odd length cycle, right? Cycle with any odd length. I'm going to come back and give you a lightning proof of that in a minute or two. Okay, so very last, well, actually, so I'm going to prove half of this for you now. If a graph contains an odd cycle, it definitely can't be bipartite, right? And the reason is this, right? That here's an odd cycle, for example. This is a cycle of length 7. We sometimes call an odd length cycle just an odd cycle. So 1, 2, 3, 4, 5, 6, 7. Well, if this was a bipartite graph, think about whether these vertices were on the left or the right. Say this one was on the left, for the sake of argument. Well then, because this is an edge, this one would have to be on the right, right? Because they can't both be on the left because this graph is bipartite. But then this one would have to be back on the left, and this one would have to be on the right, and this one would have to be on the left, and this one would have to be on the right, and now we're stuffed, right? This one can't be on the left, and it can't be on the right. So the graph couldn't have been bipartite, right? Of course, if this was an even length cycle, it'd be fine because there'd just be an edge here and it'd all work. But for odd length cycles, the graph, if it's got an odd length cycle, can't be bipartite. And as I said, at the very end of the seminar, I'm going to give you a lightning proof that the opposite way works too, right? So it's not too hard to show that a graph with no odd cycles must be bipartite, but it's a bit more work than this. Okay, so just before that, our very last concept is connectivity, and this is a really sort of obvious one, I think. A graph is connected if it's just all in one piece, right? And the way we can say that formally is that if you pick any 2 vertices of the graph, there's a path between them, right? If I can draw a path from the first vertex to the second vertex, then if I can do that for every pair of vertices in my graph, it's all in one piece, right? So we actually have seen a disconnected graph, a not connected graph already, But here's another one, right? It's in two pieces. The fancy word for these pieces is components, but I've already thrown enough vocabulary at you. I won't make you remember that one as well, right? So this one's disconnected, but of course if we had an edge here or something, it would be connected, right? So connected if it's all in one piece. Okay, so as the very last thing in this seminar, I want to give you a very rough proof of that second fact I talked about, that we saw that if a graph has an odd cycle, it can't be bipartite. Let's show that if it doesn't have an odd cycle, it is bipartite. Right, so I don't want you to stress about the details here, just see if you can follow the vibes of what's happening here. So, this is another reason I want to show it to you is it's a good example of how you can do induction on things which are not just sequences or sums, right? So I want P of n to be the statement that a connected graph with n vertices and no odd cycles is bipartite. I'm going to just talk about connected graphs because if this is true for connected graphs, it's easy to extend it to disconnected graphs because if each piece is bipartite, the whole thing is bipartite, right? Okay, so let's start with 2. A graph with 2 vertices is obviously bipartite, right? We put one vertex on the left, one vertex on the right, it's bipartite. Okay, so let's suppose that every connected graph with k vertices and no odd cycles is bipartite, and try and prove this for a graph with k plus 1 vertices and no odd cycles. So very roughly it goes like this. So take your graph with k plus 1 vertices and no odd cycles and temporarily delete a vertex. When we delete a vertex, we haven't created any cycles, right? So the remaining graph still has no odd cycles, and it has k vertices. So by our inductive assumption, we can split it into left and right parts, right? So we can divide it into left and right parts. So if here is our vertex A, what's left we can divide into left and right parts so that all the edges live between these parts. We might split what's left into multiple pieces, but that's okay, not a big deal, right? We know that the whole graph is connected, but not necessarily that it will be connected after we remove A. Okay, let's make these pieces so that we know A must be connected to one of these two things. It could be connected to both, at least for all we know, but definitely it's connected to one, so let's put that one on the left. It's connected to one because the graph is connected, right? Now, this is the interesting step. So if A is joined by an edge to a vertex on the left, I claim it can't be joined to a vertex on the right. So I reckon this edge can't happen. And why can't that happen? Well, because this piece is connected, there's a path between this vertex and this vertex. So maybe it looks like this, right? 1, 2, 3. And if this edge was here, we'd have a 1, 2, 3, 4, 5 cycle. Right? Now, I don't know that this is a path of length 3, but it must be a path of odd length, right? Because it has to go to the right, to the left, to the right, to the left, to the right, to the left, to the right to finish up. And so this argument is going to work in general. If A was connected to something on the right, we'd have an odd cycle, but we don't have odd cycles. We're assuming that. That means A isn't connected to isn't joined to with an edge, any vertex on the right, and so I can now just add A to my right side and the whole graph is bipartite, right? So that was a lightning proof that that bit is true. Again, only interested in you getting the overall idea of that. And that is all I have for you. We will slow down a bit and take some time to smell the flowers of these graphs or whatever in tomorrow. Yeah.
What's the main difference between the path length and the cycle length? I didn't quite catch up.
So I think all I was really trying to say there, in both cases the length is the number of edges, but that means that if I think of a path of length, it has two edges, but then it has three vertices. Well, sorry, so let me do it better. If I do a path of length 3, it has 4 vertices, right? But if I do a cycle of length 3, it only has 3 vertices. So you've just got to remember that the length is the number of edges, and there will be this little change in the number of vertices. So for a cycle, it's sort of obvious. You can think of the length as the number of edges and the number of vertices, but for a path, it's the number of edges, it's the number of steps.
So I was wondering, if we want to write the edge set for a directed graph,
Yeah.
instead of having it as a set A, B, we use like an ordered pair.
Yeah, so it would be a set of ordered pairs that represent directed edges. Absolutely right.
Thank you.
Thanks.